Hello everyone, welcome back to our AI series. In the last episode, we started exploring informed search strategies. Today, we'll take this further by diving into memory-bounded search methods and how heuristics can be made smarter. Trust me, this session will really connect the dots for you. Let's start with a simple challenge. Imagine your computer has limited memory. How can it still perform powerful searches? That's where algorithms like IDA, RBFS, and SMA come into play. IDA keeps only one number, the current F-cost limit. Efficient in memory, but it forgets almost everything. RBFS is a bit better. It remembers more, but still linear in memory. The drawback? It often changes its mind, re-expanding states again and again. Finally, we have SMA, Simplified Memory Bounded A. This one uses all available memory smartly. When memory is full, it discards the worst leaf node and keeps track of its quality. This way, it can regenerate it later if needed. So SMA is complete if a solution fits in memory, and it's optimal if the best solution is reachable. Pretty neat, right? Now let's think like the algorithm itself. Imagine your A. Every step you take expands a node. Some expansions are useful, others are wasted. What if you could learn from your past mistakes? That's where the concept of metalevel state space comes in. At the meta level, the algorithm learns which subtrees are promising and which ones to avoid. The goal? Reduce the total cost of problem solving by balancing computation time and path cost. Let's bring in a classic toy problem, the 8 puzzle. On average, it takes about 22 moves to solve, but the branching factor is 3, which means without heuristics, we'd look at billions of states. So, we need heuristics. Two popular ones are H1, the number of misplaced tiles. Simple, admissible, but not very strong. H2, the Manhattan distance, the sum of the vertical and horizontal moves each tile needs to reach its goal. This is also admissible and usually much better. Between the two, H2 dominates H1, meaning it always performs better or equal. For example, A with H2 can be thousands of times more efficient than uninformed search. How do we invent better heuristics? A few clever tricks. Relaxed problems. Imagine loosening the puzzle rules. For example, if tiles could jump anywhere, misplaced tiles would be the exact solution cost. That's how H1 was born. Subproblems and pattern databases. Break the puzzle into smaller parts, like solving just tiles 1, 2, 3, 4. Store all possible solutions in a database. Later, when solving the big puzzle, just look up the subproblem cost. This makes solving huge puzzles like the 15 puzzle or even the 24 puzzle drastically faster. Learning from experience. Solve many puzzles, record how far different states are from the goal, and use those statistics to train a heuristic function. This way, the algorithm learns to predict better with time. So, what did we learn today? Memory-bounded search algorithms like SMA make the best use of limited memory. Heuristics can be designed from relaxed problems, subproblems, or even learned from experience. Better heuristics directly mean faster and smarter problem solving. In the next episode, we'll explore how heuristics apply in even more advanced search strategies and real-world problem solving. If you found this helpful, don't forget to like, share, and subscribe, and drop a comment. Which heuristic did you find most intuitive, misplaced tiles or Manhattan distance?